Hello everyone. Imagine two triangles, one tiny, one towering. Their shapes are identical, but their sizes worlds apart. Now these two triangles are similar. Now here's the twist. If one triangle is twice as long as the other, how much bigger would be its area? Would it be double? Triple? No, it would be actually 4 times bigger. Let us look at similar triangles and see the relationship between their areas and their sides. For this, we need to look at this theorem which says that the ratio of areas of two similar triangles is equal to the square of the ratio of their corresponding sides. Let us look at what is given to us. It is given that we have two triangles, triangle ABC and triangle PQR, and these are similar. Now what we need to prove is that the ratio of their areas is equal to square of ratio of their corresponding sides. Here AB and PQ are corresponding sides. Then we have BC and QR and AC and PR. So this is what we need to prove. Let us start with a little construction. We are going to construct AM, which is perpendicular to BC, and PN, which is perpendicular to QR. Now, if we try to find the ratio of areas, we'll see that area of a triangle can be given by half into base into height. So, area of triangle ABC is half into BC into AM divided by area of triangle PQR is half into QR into PN. Right? Now, we can cancel this half by half, which leaves us with this BC into AM divided by QR into PN. Let us call this equation 1. Next, if we look at these two triangles, ABM and PQN, the left one in both the blue and green color triangles, we see that angle B is equal to angle Q. That is because triangle ABC and PQR are similar. Similar triangles have equal angles. Also, angle M is equal to angle N, which both of them are equal to 90 degrees, right? So these two triangles are similar by AA similarity. Now, we know that if two triangles are similar, the ratio of their corresponding sides is equal. So AB upon PQ will be equal to AM upon PN, right? And let us call this equation 2. Now, I'm going to write both of these equations on a fresh page. If you notice what was given to us initially, that these two triangles are similar. So if these are similar, the ratio of their corresponding sides is equal as well. So AB upon PQ is equal to BC upon QR is equal to AC upon PR. Let us just highlight this first proportion. Let's call this equation 3, and now I'm going to highlight this first proportion, this one. AB upon PQ is equal to BC upon QR. Now if you look over here, AM upon PN is equal to AB upon PQ. I can substitute it over here. I can write AB upon PQ here. Similarly, in place of BC upon QR, I can write AB upon PQ. So from 1, 2 and 3, from these equations, what we get is that ratio of areas is equal to AB upon PQ into AB upon PQ. That is AB upon PQ whole square. And since this is equal to BC upon QR, this ratio, I can write it as BC upon QR whole square equal to AC upon PR whole square. And this is exactly what we wanted to prove, that the ratio of areas is equal to square of ratio of their corresponding sides. Now let us look at one example. It is given that there are two triangles ABC and DEF which are similar, and their areas are 64 centimeter square and 121 centimeter square respectively. EF is 15.4 centimeter, then we need to find BC. Now we have seen that ratio of areas of similar triangles is equal to square of ratio of the corresponding sides. Since EF is given and we need to find BC, we are concerned with only this part, right? Area of triangle ABC is 64. area of triangle DEF is 1 to 1. BC is something we need to find. EF is 15.4. Now, if I just remove this square over here and bring it on the other side, on the left side, we need to find the square root of 64 and 121. Square root of 64 is 8. Square root of 121 is 11, is equal to BC upon 15.4. So, BC would be 8 into 15.4 divided by 11, which is 11.2 centimeters.